So we're going to go into rational functions. So rational functions are kind of an extension of your polynomials. What we're going to talk about is finding the domain of these functions, talking about their graphs and asymptotes. So before we start that, would you talk about a little notation? So the arrow symbol that you see here, that signifies that we are approaching something. So it means to approach. So notation x arrow 3 means x is approaching a value of 3. Or another way of saying this is that x is getting really, really close to this 3, but it's not going to equal this 3. The notation that x approaches negative infinity means that your x values are getting infinitely smaller and smaller and smaller. The notation x goes to positive infinity means your x values are getting infinitely larger and larger and larger. So this doesn't always have to be x values. You can say you have a function is approaching something. You can say a y value is approaching something. So like I said, this doesn't apply just to x, just anything that's a number that's approaching a value, that's what we're looking at. Or even an expression or an equation that's approaching a particular number. So your rational functions are a quotient of two polynomials. That is, if you had fx, which is px over qx, p and q are going to be polynomials, and p cannot be a zero polynomial, meaning q can't be a zero polynomial. I don't know why I wanted to be b today. That means that q of x cannot equal 0 for all x. It can't for some, but it can't do it for all of them. So we kind of seen this before, but the domain is going to consist of all inputs for which your q or your denominator doesn't equal 0. So what we're going to do when we're finding domain is like we did towards the beginning of class when we were talking about domains and ranges, is that we are going to look for the place that the denominator is 0 to remove those from the domain. So if we consider fx equals 1 over x plus 4, 1 is a polynomial. It's a polynomial that's just 1. The denominator is also a polynomial, x plus 3, and we want to find the domain. So what we're going to do is we are going to look at where q, or our denominator, is equal to 0. So that happens at -4. So as a quick reminder, this means that if I put in the function value of -4, I end up with 1 over -4 plus 4, which is going to be 1 over 0. And we can't divide anything by 0. This is undefined. So for some to be in my domain means that I can plug in the value and it's going to be defined. So my domain would have to consist of all numbers with the exception of -4, because that is the one which the function is undefined. So if we're going to talk about this in interval notation, this means that I have an empty spot here at 4, but I cover the rest of the number line. So that would mean that in interval notation, my domain covers from -infinity, negative infinity up to that -4. Then we go to the other side of it, -4 to infinity. And we just put a union in between it to let them just to signify that these two sets are going together to represent my entire domain. So we see here that I have a graph of the function. So the green line's a function. The blue line is representing this area I don't cross. So we said this is defined everywhere except when x is equal to -4. So what happens at -4 is that my graph for the most part is going to just get really, really close to that -4, but it's never going to cross it. So it's just for infinity getting closer and closer, but we never actually have a value at x equals -4. It's going to stay undefined. So your first problem, so if you want to, you can graph this in a graphing calculator or Desmos to see how this is going to look. But first, find the domain of the function. Then we can look at the graph. 6. So a couple of these are provided with graphs, but the same thing. Show me what the domain is. The graph can kind of help you, but not all the way. We have 3 parts to 6. So you have A through F, number 6. All of those, just find what the domain would be. And come back when you're done. All righty. So for this one, like I said, just look at where that denominator is equal to 0. So what we see is that this will need to be factored because we got a quadratic. So I need 2 numbers that add to give me +2, or sorry, multiply to give me +2, but add to give me -3. Well, -2 and -1. If we multiply them +3, if we add them, -3. So that means my zeros for the bottom would happen to be 1 and 2. So when I'm considering my domain, the 2 numbers I need to remove from my domain have to be 1 and 2 because they're the 2 that make the denominator 0. If we were to write this in interval notation, we got a hole in our domain at 1 and 2. So I have values from -infinity up to 1. I have values between 1 and 2. And I have values from 2 to infinity. So we just make sure we put those u's between them, signify that they all belong together. So for 6, A and B, you'll notice that both of them don't seem to cross this line at the y-axis, so that's x equals 0, which would make sense because in both cases, if I look at the denominator, I got x, so x equals 0. Well, automatically, if x is 0, that has to be out of my domain. Same thing, if it's x squared equals 0, set the denominator 0, well, that means then x would have to be 0 to be thrown to make the denominator 0. So my domain for both of these is all our x's with the exception of 0. So we would say we have everything from -infinity to 0, and then 0 to +infinity. So if you look at C and D, it looks like maybe here at -2 and maybe here at 1 are 2 of the places. It looks like maybe I don't have any values in my domain. Well, once again, we're just going to take that denominator of x squared plus x minus 2 and set it equal to 0. I need to factor this, meaning I need 2 numbers that multiply to give me -2, but add to give me 1. So that would be x plus 2, x minus 1. So the zeros I would have would be -2 and 1, which is what we see here. So this one matched up pretty well. So my domain is x such that x cannot be -1, 2, or 1 because those cause my denominator to be equal to 0. Or you could say it's everything from -infinity up to that -2. Then everything between, so like I said, everything here, everything between the -2 and the 1. And then everything from the 1 to infinity. So for D, that one's a little harder to tell because it looks like we've got a bit of an area here where it looks like it's kind of a gap. So, I mean, it could be I'm trying to get it to hit a certain value here and I'm not quite hitting it. There we go. So anything in here looks like a possibility. This is why I can't necessarily depend on graphs. So if we take our denominator, we set it equal to 0, we solve for x, we get that x equals 3 is where we have a hole in my denominator, or I have a hole in my domain. So it's about here. It's just this part's really close, but this part isn't. That is where we have a hole in the domain. So once again, this value has to be thrown out of the domain because my denominator is 0 there. So my domain is x, just as long as x is not equal to 3, or negative infinity up to 3, then we skip over 3, and then we go from 3 to infinity. And then for these last ones, once again, if we're going to make a guess, it looks like maybe about at -1 here, and maybe somewhere in here. It looks like 2 places that I'm missing a function value. But like I said, the graphs aren't the best way to figure that out. So we look at the denominator by setting it to 0 and figuring out where does it equal 0. If I factor this, I need factors that multiply to give me -2, but add to give me -1. So that would be x minus 2 and x plus 1, meaning that my zeros would be -1 and 2, which is almost what we had here. So let me move this one to the correct spot. Once again, domain is anything with the exception of x being -1 or 2, because that makes my denominator 0. Or we could say it's all this here. So from negative infinity up to that -2, then between that -2, or sorry, -1, because we're through here up to that -1. Between that -1 to +2, I have values. And then once again, after that 2 to infinity, just can't have any at -1 or 2. So that'd be my domain. And then for f, it looks like, once again, it's probably here in -1. So we take that denominator, we set it equal to 0. And in fact, x equals -1 is a place where the bottom is 0, my function is undefined. So the domain is x just as long as x is not -1 or negative infinity up to -1, -1 to infinity.